heating or cooling of a plate with finite thermal resistance. So, this is your 36th class, or you can regard it as a penultimate class to transport phenomena course. So, this is your TP 36. So, today we will go through the heating or cooling of a plate having finite thermal resistance. In such a case, thermal conductivity of the material is finite, and the temperature of plate is a function of space coordinate and time. In practical applications, such cases frequently occur. And our task is to represent temperature of the body or temperature of the plate as is a function of space coordinate and time. T is equal to function of x and t. So far as the practical application of such a cases are concerned, so there may be two different possibilities. There may be two different possibilities. What those possibilities are? Number one, the number one possibility is surface resistance is negligible. If the surface resistance is negligible, then surface temperature of the plate reaches the ambient temperature in a quick time. That means if the surface resistance is negligible, then the surface temperature of the plate will certainly attain the temperature of the ambient air in a very quick time. Another is which is supposed to be the most practical case, the surface temperature is finite, the surface temperature is finite and heating or cooling of an object with finite thermal resistance, that is the surface resistance as well as the internal resistance is considered. Example of such case is the quenching of hot metallic plate, in a quenching fluid, So the case that I am going to discuss today is very, very important so far as the metallurgical heat treatment processes are concerned, especially the quenching one. So, in order to solve this such type of problem, or in order to discuss such type of problem, it is necessary to formulate the problem first. Once the problem will get formulated, you have to make certain assumptions. Once the assumption will be made, then it gives rise to the differential equation which can govern the entire process. Once you have arrived at the differential equation governing for the present case, after that you have to set up the initial and boundary conditions therein. You have to solve the differential equation by taking the help of the present boundary condition, and after that you will find that the temperature of the plate is all the time a function of space coordinates and time. So, that is our main aim for today's class. So, let us formulate the problem first. So, formulation of the problem. Let us consider a case of a plate having 2L as its thickness. That means I am defining only one dimensional parameter here, that means the plate is semi-infinite in nature. So, in thickness, and heat is flowing in one direction perpendicular to the thickness, Let Ti is the initial temperature initial temperature at time t equal to 0, and is subjected to a process of quenching, and is subjected to a process of quenching in a quenching medium. Definitely that quenching medium is a fluid medium. In a quenching medium having Tf as its temperature, K is the thermal conductivity, and H is the convective heat transfer coefficient, for flow of heat from the plate to the liquid. This is the formulation of the problem. So we have to express temperature as a function of space coordinates and time, This is the problem. That you have, and you have to make certain derivation, and you have to conduct the mathematical analysis for the present problem in the today's class. So the problem that I have formulated in words, let us try to visualize through a diagram now. Let us consider this is a semi-infinite plate. And this is your center line. This is the x-axis, this is your temperature axis T, okay. This is temperature time T equal to 0, and this is T equal to T. It means path is there for the heat flow, so that the tangent drawn is this point that is running parallel to x-axis. It means the day by t by day by x should be equal to 0, and this is position at time t equal to t. This is the 2L length, which can be bifurcated in two parts, LL, because this is the center line, and here P is equal to Tf at a time t equal to infinity. The center line of the plate is chosen as the temperature axis in order to take the symmetry advantage in the temperature distribution, as I have discussed the case for the plane wall with the heat source in that case also I have chosen the center line because of in order to take the symmetry advantage about this line, that is the x equal to 0. Here also I am choosing x equal to 0 as the center line, and I am taking this as an origin to take the symmetry advantage of this temperature distribution in the present case. So, as shown in the figure, center of the plate is chosen as origin. Take the advantage of symmetry temperature distribution about x equal to 0. Now, the differential equation for the present problem. Differential equation for the present case, it should be given as d by t upon d by t, that should be equal to alpha d2t upon dx2. Let it be equation number 1, where alpha is the diffusivity and t is the scale. Now come to the next thing, that is the initial and boundary conditions. Initial and boundary conditions. The conditions are here we will transform this boundary conditions. So let us write the boundary condition side by side. So the conditions are number 1 here. Number 1, t is equal to 0, t is equal to ti. Number 2, x is equal to 0, that is the center line, x is equal to 0 times t is equal to t, and this d by t by d by x, that is equal to 0, that is the tangent drawn at this point runs parallel to the x axis according to the geometrical interpretation of dy by dx. So, d by t by d by x is equal to 0, and the third boundary condition is the application of the Fourier equation here. So, x is equal to plus minus L, that is center line. If you are approaching in this direction, then this is plus L. If you are approaching in this direction, then it is minus L. So, the x is equal to plus minus L. The corresponding Fourier equation can be given as minus plus k d by t by d by x, that is equal to h, that is equal to plus minus h t minus tf. Okay. So, these are the boundary conditions. Let us suppose these are the boundary conditions A 1, 2, 3. Now, making a substitution right now. Let us define two terms, theta and theta 1. Theta is defined as t minus tf, and theta 1 is defined as ti minus tf. So, d by theta by d by t, that will be equal to d by t upon d by t, and d by theta by d by x, that will be equal to d by t upon d by x, and d by 2 theta by d by x 2, that will equal to d by 2t upon d by x2, right. So, if these are the boundary conditions, if I am putting these substitutions, these are the substitutions. So, if these substitutions are being made, then see how this boundary condition is changing. So, corresponding to the condition number 1, t minus tf, that should be equal to ti minus tf, tf will get cancelled out. So, t is equal to 0, theta is equal to theta 1. First boundary condition will transform in this manner. Second one is the x equal to 0, t equal to t. So, d by theta by d by x equal to 0, and the third one is very simple, that is the x equal to plus minus L. So, we can write here minus plus k d by theta by d by x, that should be equal to plus minus h theta, this. Let it be the boundary condition B. Also, the governing differential equation, that is the equation number 1, will also get changed if substitutions can be made. So, what should be the format of the equation number 1? That is also a thing of prime concern, and this equation can be transformed as d by theta by d by t, that should be equal to alpha d by 2t by d by x2. Let it be question number 2. Now, we have the last task to perform. It means we will solve this differential equation number 2 with the help of the boundary condition B 1, 2 and 3, in order to arrive that the temperature distribution of the plate or temperature distribution of the plate is a function of space coordinate and time. So, solution of the differential equation number 2. So, the solution of differential equation 2 by the help of initial and boundary conditions B 1, 2, 3. It will give rise to the temperature history of the plate. Let us try to proceed in order to solve this differential equation number 2. Keep these conditions in view. Now we will try to solve this differential equation. So, here the separation of variable techniques is used. Separation of variable can be used assuming theta is a function of x and t, capital S and capital T, where x is a function of x only, x, better to write here y, not t, x and y. So, where xx and yt are respectively the functions of x and t only, x and t only. So, let it be equation number 3. So, from the equation number 3, deba theta by deba t, that should be equal to x deba y by deba t, okay, and deba theta by deba x, that should be y deba x upon deba x, or d2 theta by dx2, that is equal to y d2x by dx2. Hence, from equation number 2, put this equation number 2 in this equation number 2, that is deba theta by deba t, that is x dy by dt, that should be equal to alpha d2 theta by dx2, that is alpha y d2x by dx2. Or we can write 1 by alpha y that is equal to 1 by x d2x by dx2. So, as in the case of the analytical solution of the Laplace equation in the separation of variable technique, let it be equal to minus lambda square, where lambda square is a constant. So, minus lambda square is a negative constant. So, taking the first ratio, we obtain the equation deba y by deba t plus lambda square alpha y, that should be equal to 0. Let it be equation number 4. And taking the second ratio, deba 2x by deba x2 plus lambda square x 0. Let it be equation number 5. Now, the solution of the equation number 4, so the solution of the equation number 4, solution of equation 4 is y is equal to a e to the power minus lambda square alpha t, and solution of equation 5 is x equal to b cos lambda x plus c sin lambda x. So, theta, that is equal to x into y, okay. So, that is equal to b cos lambda x plus c sin lambda x into y has a value a e to the power minus lambda square alpha t. So, that can be written as b into a cos lambda x plus b into c sin lambda x into e to the power minus lambda square alpha t. That can be further written as, let b a equal to b dash cos lambda x plus c dash sin lambda x into e to the power minus lambda square alpha t. So, this is the expression for theta. Let it be equation number 6. Let it be question 6. So delta theta by delta x value, that should be equal to, so you have not considered the t variable now for differentiation. So that will come as lambda b dash sin lambda x with minus sign plus lambda c dash cos lambda x. So the value of delta theta by delta x at x equal to 0, that is equal to e to the power minus lambda square alpha t into this quantity will be equal to 0 and this quantity equal to 1. So that is equal to lambda c dash. Now putting the boundary condition B1, now putting the boundary condition B1, B2, now boundary condition B2, initial and boundary condition B2, what was that? That at x equal to 0, the delta theta by delta x equal to 0. So imposing this boundary condition here, we can write e to the power minus lambda square alpha t into lambda c dash, that should be equal to 0. Now since this quantity cannot be equal to 0, lambda cannot be equal to 0, so c dash equal to 0. So the value of theta comes as, theta comes as b dash cos lambda x, into e to the power minus lambda square alpha t. Let it be question number 7. This should be abbreviated as 7. So let it be question number 8 now. So theta at x equal to L, that should be equal to b dash cos lambda L into e to the power minus lambda square alpha t. So delta theta by delta x, that is equal to e to the power minus lambda square alpha t into lambda b dash sin lambda x with minus sign. So the value of delta theta by delta x at x equal to L, that is equal to e to the power minus lambda square alpha t minus lambda b dash sin lambda L. Let it be question number 9. Now we proceed from the equation number 9 again, and we will refer now the boundary condition B3. Now we will refer to the boundary condition B3. So referring to initial and boundary conditions, boundary conditions B3. What was that? For x equal to L, so we can write minus k day by theta by day by x equal to h into theta at x equal to L. This is also at x equal to L. So put that here, implies that day by theta by day by x at x equal to L, that is equal to h by k theta at x equal to L, or this value e to the power minus lambda square alpha t minus lambda b dash sin lambda L, that should be equal to minus h upon k, and the value of theta at x equal to L I have evaluated already earlier. That value was, you can see from the previous note, e to the b dash e to the power minus lambda square alpha t into cos lambda L. So e to the power minus lambda square alpha t, this will get cancelled out, b dash will get cancelled out, or we can write cos lambda L by sin lambda L, that should be equal to, and this minus will also get cancelled, that is equal to k divided by h equal to k divided by h into lambda, that is equal to k lambda by h. That can be further written as k upon h into L into lambda L. This quantity k by hl, what is that? hl by k is the Biot number. So k by hl is equal to 1 by Biot number. So that is equal to 1 by Biot number into lambda L. Let it be equation number 10. This equation number 10 is a transcendental equation, and which have so many values of lambda here. So cos lambda L is by sin lambda L, that is equal to cot lambda L. So the equation number 10 is a transcendental equation. Equation number 10, it is a transcendental equation, then there may be infinite number of solutions. There may be infinite number of solutions. There may be infinite number of solutions or values of lambda satisfying it. Okay. Such values are called eigenvalues. 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 Designated as lambda 1, lambda 2 up to lambda n and so on. The complete solution of the equation number 10, the complete solution of equation number 10 will be the sum of all the solutions corresponding to each lambda value, eigenvalues. Okay. Now the equation number 8 gives, so we have arrived at the situation where the eigenvalues for the transcendental equation that has been expressed as a solution to the differential equation pertaining to the problem. So we have to express it in terms of a series right now. So for that, so the equation number 8 gives, equation number 8 gives that is the sum of all the solution theta is equal to summation n equal to 1 to infinity power minus lambda square alpha t bn dash cos lambda nx. Let it be question 11. Question number 10 can be used to evaluate lambda 1, lambda 2, lambda and so on b1 dash, b2 dash, so on bn dash are selected to satisfy the condition, that is the first condition, that is theta equal to theta 1 at t equal to 0. Okay. Help of this boundary condition, with the help of this boundary condition, equation number 11 can be represented as theta is equal to theta 1, that is equal to summation n equal to 1 to infinity e to the power minus lambda square alpha into 0 into bn dash cos lambda nx. So theta 1 comes as summation n equal to 1 to infinity, this is equal to 1. So bn dash cos lambda nx. Let it be question number 12. Or multiplying both the side by the cos lambda nx, we will get theta 1 cos lambda nx, that is equal to summation n equal to 1 to infinity bn dash cos square lambda nx. So utilizing the concept of that the definite integral can be written as a limit of a sum, this equation can be further written as, let us see question number or starting from here again, we can write theta 1 cos lambda nx dx integration from 0 to L, that should be equal to integration from 0 to L summation n is to 1 n is equal to 1 to infinity bn dash cos square lambda nx dx or theta 1, this is the sin lambda nx by lambda n 0 to L, that should be equal to, keeping bn dash outside, integration 0 to L cos square lambda nx, that is equal to 1 plus cos 2 lambda nx divided by 2 into dx. Carrying out the integration further, or we can write theta 1 sin lambda nl by lambda n, because sin 0 0, that is equal to bn dash integration half dx 0 to L plus half integration cos 2 lambda nx dx, that is equal to bn dash, and this is equal to L by 2 plus 1 by 2, here sin 2 lambda nx divided by 2 lambda n, integration from 0 to L, that can be further written as bn dash into L by 2 plus half 1 by 4 lambda n, and this is equal to sin 2 lambda nl into 0. So that can be written as bn dash into L by 2 plus, this can be sin lambda nl cos lambda nl divided by 2 lambda n, thus, or we can write theta 1 into sin lambda nl divided by lambda n, that should be equal to bn dash into half into lambda nl L plus sin lambda nl L cos lambda n L divided by lambda n. So this lambda and lambda n will get cancelled out. So the b n dash value is equal to 2 theta 1 sin lambda nl divided by lambda nl okay. This lambda n will get cancelled out. 2 theta 1 sin lambda nl divided by, this 2 will go there, divided by lambda nl L plus sin lambda nl L cos lambda n L. So this is the value of the bn dash. So this is the value of bn dash that we have obtained, that is equal to 2 theta 1 sin lambda nl divided by lambda nl plus sin lambda nl cos lambda nl. So let it be question number 13 now. From question number 13 and the question number 11 now. Now from the equation number 13, now from equations 11 and 13, theta can be expressed as summation 1 n equal to 1 to infinity e to the power minus lambda square alpha t cos lambda nx into b n dash value into root theta 1 sin lambda nl divided by lambda nl plus sin lambda nl cos lambda nl. That can be further written as 2 theta 1 summation n equal to 1 to n equal to infinity sin lambda nl divided by lambda nl plus sin lambda nl cos lambda nl, this quantity, into e to the power minus lambda square alpha t into cos lambda nx So theta by theta 1, which will express you the temperature profile in the quenching plate, that is equal to theta by theta 1. If you take the transformed variable to the original variable right now, so it can be written as theta, that is T minus Tf divided by Ti minus Tf, that should be equal to 2 summation n is to equal to 1 to n is to infinity sin lambda nl divided by lambda nl plus sin lambda nl cos lambda nl into e to the power minus lambda square alpha t into e to the power minus lambda square alpha t cos lambda nx. Let it be equation number 14. Now visualizing the equation number 14, you can easily see equation number 14, it states that temperature history of the plate states the temperature history, better right, states the temperature history of the plate as a function of x and t. This was the thing which was to be arrived, that how the temperature history of the plate can be stated as equal to a function of space coordinate and time. The second thing, the last thing in this class is how the graphical solution of the cot lambda L is equal to 1 upon Biot number into lambda L can be arrived. This is the most important thing for the time being here. Geometrically, this is solved through the basic trigonometrical thing in this manner. Here this is lambda, and along this side, the left hand side, that is the cot lambda L, is put up here. This line corresponds to lambda equal to 0, take another line lambda is equal to L, sorry, lambda is equal to pi upon L, sorry, pi by L. Another line this corresponds to lambda is equal to 2 pi by L. Next line this corresponds to lambda is equal to 3 pi by L. These are the expressions, these are the graph for the y equal to cot x. Yes. If you put the right hand side here, this will represent a straight line, this will pass through this point. This is the right hand side, that is equal to 1 by Biot number into the lambda L. This will cut all these curves at a point. Take the perpendicular from here, from this cut point. It will give you the first eigenvalue lambda 1. This will give you the second eigenvalue lambda 2. This will give you the third eigenvalue, that is lambda 3, and so on. This is the value, this is the method by the virtue of the eigenvalue in the present case can be determined on geometrical ground. Now, dear students, this completes your transport phenomena course. Up to the extent that you are possible, I have completed. In the next class, I will try to discuss some of the numerical problems, and also as a consequence to this class, I will try to put up some emphasis on the Heisler diagram. The Heisler diagram is basically used to determine the center line temperature on an industrial scale. I will try to provide you some ideas regarding the utility of the Heisler diagram, how this diagram can be made, and how the temperature of the quenching plate can be determined if the Heisler chart is available with you. Again, this type of concept and the concept that I am going to deal in the next class, that will be of immense importance so far as one of the lab of your transport phenomena, that is the cooling of ingot, is concerned. In cooling of ingot experiment, by taking the metallic ingot, you have to evaluate the value of the convective heat transfer coefficient on the surface and the thermal conductivity of the material. So, we will find that how Heisler chart can be made applicable in order to arrive at the determination of such practical quantities. I will also put up some emphasis on the numerical problem related with the rectangular fins, the lumped heat capacity analysis, and some numerical problem related with the Heisler diagram. So, in the next class, that will be your last class of your transport phenomena course. I will try to give you some flavor of the numerical problem related with the heat transfer. Thank you.